Welcome back. In this lesson I'm going to review the tallying procedures for calculation of the neutron flux in non-analog simulations. So we have been already working with the neutron flux before in the previous lessons, but let me just remind you the definition of the neutron flux. So the neutron flux actually depends on the position in the system, and the neutron energy is given by the product of the neutron concentration. The neutron concentration is dependent on the position in the system, so from there comes the dependence on the position and also on the energy of the neutron. And the concentration of the neutrons is then multiplied by the velocity of the neutrons. The neutron velocity is dependent, of course, on the neutron energy. So the dependence on energy also comes from here. You may know that another quantity exists which is called the angular neutron flux, which is a neutron flux which depends also on the direction, omega, on the omega vector. We are practically never interested in the angular flux in terms of the results of the Monte Carlo simulation. The angular flux is commonly used in order to solve the deterministic transport equation. However, that is only because the deterministic transport equation cannot be solved without considering the angular dependence of the neutron flux. So we are going to be interested only in the so-called total flux, that is basically integrated over all the directions. So we are going to consider the dependence on the position in the system and the neutron energy. So if we have a system, we may want to calculate the neutron flux in certain position in the system, for instance here, for neutrons with a specific energy, for instance 1 MeV. Now imagine that the system is very large. It has for instance several meters across, and that may be a problem, because if you simulate randomly neutron histories, you may be practically sure that none of the neutrons will cross exactly the position that you want to calculate the neutron flux at. And even if it does, it will surely not have exactly 1 MeV. So we can never get the dependence of the neutron flux on the position and the energy exactly. We have to make some simplifications. So what we do, we need to discretize the space of the system. So we have to superimpose some spatial mesh on the system, and we cover the dependence of the neutron flux only within these zones. So we will have the zone-wise dependence of the neutron flux, and the same we can do with the energy dependence. So we can again superimpose an energy mesh over the whole energy spectrum, and we will calculate the energies within the energy mesh. So you can imagine, if you want to have very fine mesh superimposed on the system and also on the energy, then you will need much better statistics in terms of the number of the neutron histories that you have to simulate. The finer the spatial mesh over the system and the energy mesh, the more neutrons you need to simulate in order to cover the dependence accurately. The actual estimation of the neutron flux can be done by... In one of the previous lessons I have already derived the physical meaning of the neutron flux. So when we actually calculate the neutron flux within specific space region, so for instance the flux which is integrated over this space zone and integrated over a specific energy bin, the physical meaning of this flux will be the combined distance that the neutrons would travel within this specific zone and within the specific energy bin. So both of these estimators are actually based on this interpretation of the physical meaning. Let's have a look at the collision estimator for the neutron flux first. The collision estimator is using a counter. It's a quantity that we can call Fc. It's counting the neutron flux for specific space bin within the space mesh and the energy bin. So I accounts for the space bin and the J index accounts for the energy bin. Now this counter is set to 0 at the beginning of the active cycles. So the neutron flux is only calculated over the active cycles. You remember that the inactive cycles are only used for the converging of the neutron flux. So once those are over, we start to simulate the active cycles and we start to evaluate all the results. So if the flux is required as one of the results, then the counter is set to 0, and every time a collision is simulated of any neutron history, the counter is increased by this value. It's a ratio of the statistical weight of the neutron and the total cross-section, total macroscopic cross-section, which is evaluated at the energy of the neutron. So let's say that the neutron arrived to the collision, and at this point the counter is going to be increased by this value. So what does it actually mean? 1 over the total macroscopic cross-section is the mean distance between the collision. So it's going to take the mean distance between collisions, and this is multiplied by the statistical weight of the neutron. Remember, all the results need to be always compensated, so we need to multiply by the statistical weight. Now there are counters for different spatial zones and the energy bins, so you need to find out at which spatial zone the collision takes place and to which energy bin the neutron energy belongs to. So you need to identify the appropriate counter and increase the value of this counter by this number. Most of the Monte Carlo codes normalize the neutron flux at the end of the simulation by the number of neutron histories that were simulated in all the active cycles. So that is this H number here. H is the total number of histories in active cycles, and some codes also normalize the neutron flux by the volume of the spatial zone and the width of the energy bin. However, here you have to be very careful, because very often the normalization by the volume of the spatial zone and the width of the energy bin is not done by default. Sometimes you have to instruct the code in the input file to perform this normalization for you. Let's have a look also at the second estimator, the path length estimator for the neutron flux. I'm denoting the counter for this estimator as Fp, and again we have different counters for different spatial zones and for different energy bins. Now once the neutron collides, the spatial bin and the energy bin need to be found, and the appropriate counter is increased by this number. So this is a product of the statistical weight of the neutron, and then we have a distance that the neutron travels within the space bin. So this estimator is actually more straightforward than the collision estimator, because it really combines the distance that the neutrons travel within the different spatial bins. Now again, the counters are normalized at the end of the simulation, so it's divided by the total number of all neutron histories that are simulated during all the cycles, the active cycles. And then again, some codes, they also normalize it by the volume of the spatial bins and the width of the energy bins. Nevertheless, again, you have to check whether this normalization is done by default by the code. If not, you have to make sure that it is done. And that is all for now. Have a nice day.